Hello and welcome to another chemistry topic together. As you can see, we're on Unit 9, Day 3. If you're doing this when the video was originally assigned, it is April 20th. And our topic today is something called the VSEPR theory, which is how chemists say it. I know it looks like it should be VSEPR. VSEPR theory is our focus for today. So if you are taking these notes for Killing and Try 3, go ahead and set up your focus notes page. If you're watching these notes at any other time or for any other reason, I welcome you. I'm excited to do some chemistry together with you. So the essential question for today is, how do I determine the shape and polarity of a molecule? So these notes are assuming you already know some things about molecular structures and about polar versus nonpolar, covalent bonding. Those are some of the background things you might already know, though we'll review a little bit of that, but hopefully you kind of have a background in Intro to Bonding, ready to start thinking about three-dimensional molecules. Pause the video, finish setting up your focus notes. Come on back when you're ready. All right, so let's first of all figure out what this VSEPR theory thing stands for. It's an acronym and it stands for valence, shell, electron, pair, repulsion. So we're focusing on the valence electrons. So valence shell are those outermost energy level electrons, highest occupied energy level. And we know that pairs of electrons, because they're both negative, would want to repel. They want to stay away from each other. So because electrons are trying to stay away from each other, molecules bend the geometry or the shape or the angle of their bonds so that those electron pairs can be as far away from possible on the central atom. So you've got something kind of in the middle of your molecule. All the pairs of electrons around that central atom are trying to stay as far away from each other as possible. And that's because same charges repel. So the pairs of electrons are trying to stay away from each other, so they bend their angle of their bonds, change their three-dimensional shape to make that as comfortable as possible. So I'm going to show you the VSEPR shape sheet that has some different shapes on it. Go ahead and you'll download that sheet from Schoology and put it into Notability. And I'm also going to show you a website that shows it a little better. And if you want to play with this website more, I do have that link on Schoology. So let me exit this presentation and go to these two screens. So this is the VSEPR shape sheet, and notice it's got some different names of shapes. It shows you the shape that's supposed to be 3D in two-dimensional, and look at it focuses on the central atom. So if you have a central atom and there's two atoms on the central atom and there are 0 lone pairs, you get this shape. So you can see it right here that it looks linear, right? So if I click that, it says linear. I have a central atom, 2 atoms bonded to that central atom, no lone pairs. So this is staying as far away from each other as it can. In fact, we would say that this was 180 degrees away from each other, right? A straight line. So if I here show bond angles, so this pairs of electrons are as far away as they possibly can, straight a line away from each other, 180 degrees. All right, well now what if I keep 2 atoms on the central atom, but I add a lone pair? So if I add 1 lone pair, look at what just happened. The angle, the shape of my molecule just changed. Look, it's called bent now. So instead of being 180 degrees away from each other, because there's now this third thing that's repelling, these, remember, are electrons, now you get 120 degrees. So they're not as far away from each other as they were in linear because there's another pair of electrons that they're trying to repel or stay away from. So that's kind of the idea. Now, let's say instead of having this lone pair, so I'm going to get rid of that, let's pretend I have a third atom on the central atom. So I'm going to put another bond. Well, notice it looks kind of similar in shape to that bent one I just showed you, but take a look at this. It is all in the same plane is what that's called. So this is called trigonal planar. Trigonal because it's got 3, right? Tri. And then planar because look, if I try to move this three-dimensionally, you can see that everything is all in the same plane of the group. All right, I know that you can hear my phone ringing now. I'm going to ignore it because I'm going to keep going with my lecture. All right, so because everything is in the same plane, that's where trigonal planar comes from. But if we want to look at the bond angle, you'll see that it is also around 120 degrees because, again, they're trying to all stay away from each other. So if I get rid of that bond and go back to the lone pair, notice that we don't call it trigonal planar because this is not an atom, it's just a lone pair of electrons. All right, well, let's go back to these shape ideas. What if I have something called tetrahedral? Tetra meaning 4 and no lone pairs. So I'm going to get rid of that lone pair and I'm going to add 2 more bonds. So now you can see, oh, okay, so look at this. So now I've got this sort of, it kind of looks like one of those massagers. Maybe you've seen one of those that you can like roll on your back or on your muscles. So that's kind of the idea. So you get this thing called a tetrahedral. It's got 4 sides, 1, 2, 3, and then 4 would be this one kind of in front of you. So here, let me show this. So like 1, 2, 3, and then back there would be 4. That's called tetrahedral. And then it just keeps going. Notice we've got another version of bent. So let me get rid of this and put 2 lone pairs on it. So we still end up with that bent shape. These atoms are staying as far away from each other as they can. So we just have another version of bent. And then there's just other examples. I'll let you play around with those if you want to. But notice that we're always focused on that central atom. How many atoms on the central atom? How many pairs of unshared pairs on the central atom? So not how many electrons, but like this was 2 atoms and 2 lone pairs. 2 and 2 is this version of bent. That is the idea behind the VSEPR shapes, trying to think about what they would look like 3-dimensionally instead of just what they would look like on 2 dimensions, right? Okay, so I'm going to go back to my presentation here, and then I'm going to have you take a moment to kind of process what you just heard and do a level 1 question. So thinking about what you saw, what you heard about our notes so far, maybe what does VSEPR stand for? That'd be a very wonderful, basic level 1 kind of question, or come up with your own. Pause the video, come back when you're ready. Okay, so the next piece of the VSEPR theory is not just the shape of it, but what about the polarity of the molecule? So you've got 2 choices. Is it polar or nonpolar? And the reason we care about that is because it's going to help us understand some more things about properties of molecules, especially solubility and melting point. Like, what does it mix with and how much energy does it take to break apart and melt the structure? That kind of stuff has to do with polarity of the molecule. Is it polar or nonpolar? And you're really thinking of it like tug of war. So if the central atom is being pulled evenly in every direction, we would say that's a nonpolar molecule. So here's a visual. So pretend this is an atom or a bond, this is an atom or a bond, this is another atom, and there's your central atom. So if they're all pulling evenly in every direction, we would say that whole molecule is nonpolar. It doesn't matter what kind of a bond this was. If this was a weak polar bond or a very polar bond, the whole molecule will be nonpolar because it's being pulled evenly in every direction. If it is not being pulled evenly in every direction, that would be a polar molecule. So like, for example, if this atom was much weaker than these 2 atoms, it would not pull as much. So then this would be an uneven pull. So then this would be a polar molecule. There would be partial positives and partial negatives throughout the molecule, and that will affect the properties of that molecule. So pulled evenly in every direction is nonpolar because there's no place where there's a different pull. A polar molecule is if one atom is different or if there's lone pairs, they pull differently than other atoms. So it's the shape of the molecule and the type of bond that's present that will determine if it's polar or nonpolar. And we'll do some examples with that to make that make a little bit more sense. But a couple hints I have for you. If you have a nonpolar bond within your molecule, it has to be a nonpolar molecule, no matter what the shape is, because nonpolar means there's no place that's pulling differently. So if the bonds aren't pulling differently, the molecule can't have any places that are pulling differently. So that's a nice little shortcut. But if it is a polar bond, it could be a polar molecule or a nonpolar molecule, depends on the shape. Because if the shape is even in every direction, even though there's polar bonds, if those polar bonds are the same in every direction, it will be a nonpolar molecule. If it's a polar bond and it's not the shape even in every direction, then that will be a polar molecule. And another little hint for pre-AP level examples, most of the time if there's lone pairs present and polar bonds, it's going to be a polar molecule. So that's kind of a little shortcut, but I still want you to always think about the bonds that are present and the shape that's present to see if the whole molecule is polar or nonpolar. Go ahead and do a level 2 question. Kind of think about the stuff we just talked about, polarity of bonds versus polarity of molecule, something like that. Level 2, draw, explain, compare and contrast. Come on back when you're ready. So now it's time for some examples. So we are going to do two examples that will kind of walk you through how we use VSEPR and how we figure out VSEPR. So first we need to know the formula of the molecule. And then we're going to show its representation or its structure, or its Lewis dot diagram. So if we figure this out, water has 8 valence electrons total to spread around 2 hydrogens and 1 oxygen. So we get a structure that looks like this. 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Hydrogen only needs 2 to be stable, and oxygen has 8. So that's good. So then now what we would do is we would look at that shape sheet. And so I'm going to go back to that shape sheet quick. Remember that we have 2 lone pairs and 2 atoms bonded to the central atom. So let me go back to this. So 2 and 2. 2 atoms on the central atom, 2 lone pairs. So then it is a bent molecule. All right, so let me go back to this screen here. So bent molecule. The polarity of the bonds, this is where you look up the electronegativity values on the periodic table. You show work to show the difference between them. I'm doing this for you, but if you need a review of this, look back in your notes for electronegativity values. If you're watching this in Killinan's class, that was day 1 of this unit. So you look up, this is the electronegativity value for oxygen, the electronegativity value for hydrogen, subtract them. 1.4 difference means a 30% ionic character. 30% is in our strong polar bond. So now I know that this is a polar bond and this is a polar bond. Okay, well now we got to think of that tug of war. So I'm going to exit one more time and I'm going to come back to this thing. So let's create, so we've got this bent shape. This is even the one that we needed. 2 lone pairs, 2 atoms. Take a look at this. If I turn it, does it look the same in every direction? So as I spin it here, does it look the same every time I spin it? Does this look the same as when I go like that? Nope. Does this look the same? Does this look the same? So if I can move the molecule and it doesn't look the same in every direction, that means that this is not an evenly pulled molecule. This pull is different than lone pair pull. So because this is a polar bond in water and the shape is not even in every direction, okay? So let me go back to this here. That means that this is a polar molecule. So because this is not even in every direction and because your bond is an uneven pull, the whole molecule is polar. And it turns out that that's really a little spoiler alert. That's why water is so interesting, because it's really polar. It can mix with things that are ionic. It can mix with things that are polar. It just has lots of interesting properties because of that polar molecule with the shape of water. Okay, let's try another one. How about this one? CO2. So instead of H2O, CO2. So if you look it up on the periodic table, oxygen both has 6 valence electrons, and there's 2 of them, so that's 12, plus carbon has 4, so that's 16. So we're going to need some fancy sharing, 2 double bonds. Let's check to make sure that we only have 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. This oxygen has 8 valence electrons. This carbon has 8 valence electrons because 1, 2, 3, 4 bonds is really 8 electrons. And then this oxygen has 8 valence electrons. All right. So then if we think about the shape, I have central atom. I have 2 atoms on the central atom. And look, there's no lone pairs on the central atom. So let me go back to my shape sheet. So I have 2 and 0. 2 atoms, 0 lone pairs. Oh, the shape is linear. Okay. So let's fill that in on our sheet. So we got that already filled out. So linear. Now we're going to figure out what the polarity of the bonds is. So I look up the electronegativity value for carbon. I already knew that oxygen was 3.44. I subtract them. I get 0.89. That makes a 19% ionic character. 19% is a weak polar bond. Okay, so this is a weak polar bond. This is a weak polar bond. But then now we need to think, is it tug of war? Is it even in all directions? So we can go back to our PhET site here. So I'm going to get rid of those lone pairs. And instead, I have this shape, right? 2 atoms. Yeah, they technically, if you want me to, I could put these in here. All right, so technically they were double bonds, but they don't change. This is the same as if this was a single bond. So what I have here, I have 2 atoms on the central atom, no lone pairs, linear shape, and then look it. There's really no way I can make it look different. You're always just going to have that thing in the middle, these 2 things on either side. I mean, sure, I can make it top or side or a 3-dimension. I can try to go like that. But no matter how I move it, you always just have the all 3 atoms in a row, in a line, linear, right? So then in terms of it being considered polar versus nonpolar, we would say this is nonpolar. So even though this is a weak polar pull and this is a weak polar pull, they balance each other out because of the shape. So carbon dioxide is actually a nonpolar bond and that or molecule. So then that would tell us some things about why carbon dioxide mixes with some things and not with others. It would tell us some more about its properties. And that's actually what you're going to do for the lab in this unit is look at things that are polar versus nonpolar. What kinds of properties would they have? All right. So that idea of this is how we use VSEPR to figure out the polarity of the molecule by looking at the bonds and the shape, kind of reviewing some other things we've done. Now this is the new part, the shape, and then also the polarity of the whole molecule. All right. Go ahead and start making a connection to a level 3 type of questions, a predict, a defend, something like that, something level 3. And then you'll also do your summary in a little bit too. Pause the video, come on back when you're ready. All right, that brings us to the end of this day 3 of this unit. Here's your to-do list. Go back and finish any COSTA questions so that you're actually taking time to think about the notes, process them, and same with the summary so that you answer your EQ. Can you answer our essential question to summarize what you learned today? I do have a practice assignment about VSEPR. It looks very similar to that chart we just, like this. It looks very similar to this worksheet, or the worksheet looks very similar to these examples, just to kind of help you know what to expect. And then remember, there's unit practice problems. You get immediate feedback because you can check the answers, so you know what you might need to study again or ask for help on to just help you move forward and feel confident with this material. All right, and then we'll see you at our next Zoom meeting. Thanks so much for listening and learning more about chemistry. Talk to you next time.